Welcome to today's virtual tech talk. My name is Mary Benyon, and I will be your moderator for today. So this is our last talk of 2020, and if you've been able to attend previous sessions, we hope you found them informative and interesting. We're busy putting together the 2021 schedule, and we're looking forward to continuing to bring the very latest from ARM engineering and, of course, our AI ecosystem partners. We would love to hear from you as well, what's working, what's not, what topics you'd like to see covered. If you can take a few moments after today's presentation to fill out our survey, we'll enter you in a drawing for a free Arduino Nano BLE33 board, and we'll be giving away 2. So if you want to win one, you have to fill out the survey. So I'm really happy to present and introduce SLAMcore today. We have Owen Nicholson and Paul Brasnet, who will be talking to you today. So just a little bit about Paul and Owen. Owen is the CEO and co-founder of SLAMcore and is a specialist in technology commercialization. He spent some time at the Ministry of Defense, where he specialized in early stage technology. He was also at the consumer electronics company Dyson, where he oversaw their external research program portfolio. And most recently, he has led SLAMcore through a trajectory of 3 funding rounds, raising over $10 million. And he has grown the team to over 20 specialists in computer vision and embedded software. And Paul, not to be outdone, is VP of Product Strategy at SLAMcore. And prior to this, Paul was at Imagination Technology, building and leading research and architecture teams, developing technologies for computer vision and AI. Paul has around 20 patents. Is that enough? I think you need more, and has a Master's of Engineering and PhD degrees from University of Bristol, UK. So welcome, Owen and Paul. I'm really happy to have you here.
Hi, Mary. Absolutely great to be here.
Yeah, so how are you guys doing today?
Doing really well, yeah. Really excited to tell you about what we've been up to.
Awesome. So before we get started, you guys wanted to ask, I guess you've just moved offices. And wanted to understand also, since the holidays are right upon us, if you have any plans during the season.
Yeah, absolutely. So we've actually just moved offices last week. Just a note, it's a really good time to get good deals in office space at the moment. So we took advantage. Being a company who works with robots, we need space in central London. It's hard to find, but we're now in our new offices, and today I'll actually be giving you a tour of it. So, but from quite an interesting perspective.
I love it.
That's a bit of a hint.
Yes, I see Barry in the background, right? Awesome. Okay, well, let's, I guess we can jump right into it. So for everybody attending, please feel free to ask questions during the talk. Just put them in the Q&A box, and we'll get to those during the session. Paul will jump in with questions and ask them during Owen's prezo. And then once they're done, we're thinking we'll just open the mics for you to ask any questions directly of Paul and Owen. So if you just raise your hand, we'll get to you and we'll open your mic and you can go ahead and have a chat with these guys. So, all right, it's you, Owen. I will let you take it away.
Brilliant. Well, thank you so much for the invite today. Just let me know if all the tech is working. And if you can hear me okay. So as we introduced, my name's Owen. I'm the CEO at SLAMcore, and I'm joined today by Dr. Paul Brasnet, who's our VP at Product. So SLAMcore, we provide vision-based positioning, mapping, and perception software for companies who want to deploy robots and machines with the next generation of spatial intelligence at the edge. Bit of a mouthful, but ultimately we're trying to help robots understand their space. So it's a real pleasure to be here today, and thank you for the invite, Mary and the ARM team. So before I jump into things, our full disclosure, I'm not a deep silicon guy. I'm, if anything, a recovering astrophysicist turned entrepreneur, but I have been working in the space of machine vision for over a decade. So although I'm not a technical expert, I would like to share with you my views of this landscape, but also the way in which this technology can be used to enable some really exciting and powerful products. If things go well, hopefully we'll be invited back and our technical team can come and give you a real under the hood view of what's going on within the SLAMcore technology. But today I'd like to focus on the overarching concepts behind SLAMcore, the technology that we have been building, and how it works at an architectural level. So at the end of this presentation, I hope that you can leave with a new appreciation for what's possible. And hopefully when you return to your day jobs, perhaps you can see how your work could contribute to helping to make this happen. So let's start with a bit of history. We were originally founded by myself, to be honest, the business guy, and 3 genuine leaders in this field of machine vision. So in 2014, we were all working together in the Robotic Vision Lab at Imperial College London. So Dr. Zajkovic was our first PhD student placed there. Dr. Lutenegger joined from ETH Zurich as the deputy director, and Professor Davison, who's one of the most respected academics in this field, was the director. Now, during the first couple of years, we had a near constant flow of companies approaching us and asking if we could help them integrate vision into their robotic stack. And as an academic lab, we could really only offer a PhD or point them at some papers. So they needed solutions today, not in 4 years. And that was really the genesis behind SLAMcore, thinking there's a real need here. So in 2016, we took the plunge and we founded SLAMcore with a simple mission to dramatically reduce the barrier to entry for companies looking to integrate autonomy into their stack. It's a bit punchier, that one. So I quit my job at Imperial to become the CEO, and the 4 of us hit the road looking for VC funding. So the rest is history, but I'll tell you about what we've been up to. So today we have raised over $10 million in VC capital, built a team of nearly 30 incredible engineers and scientists. Between them, we have 50 patents, 20 of which from Paul, 500 papers and 50,000 citations. This is what the team have done in their careers so far. We had a great year announcing a number of partnerships with top hardware companies, including with ARM. And after a number of rounds of competition, we were awarded the top startup award by the Edge AI and Vision Alliance. So really excited to win that. And this is really what we've been doing for the last 4 years. This year, really probably the most exciting thing is that we've built out our core platform, our core technology that we'll be using to take our product to market. And today, I'd like to really show you what's possible with this technology through a series of live demos and use it to describe the overarching architectural design of a vision-based spatial perception system. Now, this really is my only slightly salesy slide. We can provide access to a limited range of features that I'll show today through our public SDK, which you can use for prototyping and development. And if you're interested in more advanced features, then come and talk to us about our Visionaries program. But let's skip that because I want to concentrate on the tech today. Okay, so before that, let's just give you some context of the opportunity. The robotics market is already here. They say the revolution is coming. Actually, no, robotics are already here. It's big and it's achieving double-digit growth. And it's made up of hundreds, if not thousands, of sub-verticals. And there is genuinely a real revolution starting in this space because the industry is growing up. It's moving from silos to supply chains and from a handful of niche players to an ecosystem of partners driving standardization across the hardware, software, and regulation pieces. And what's more, without robots, the AI revolution is really just brains in jars because they're physical. They can interact with the real world. And I genuinely can't think of a more exciting or rewarding space to be working in. Okay, so for a machine to have full spatial understanding, it needs to be able to reliably answer these 3 questions. Where am I? What is the shape of the world? And what are the objects around me? And the biggest cause of failure for an autonomous machine is when they get the answer to one of these things wrong. So over the last few years, I've worked with literally hundreds of robotics companies, and there's a very consistent story. They all use a wide range of sensors to try and answer these 3 questions, but pretty much for all serious deployments, expensive lidars are used because they're the only thing that provides reliable enough positioning to operate in commercial settings. But not one of these companies I've talked to are actually that happy with their solution. I'm yet to find one that doesn't want to dramatically reduce the cost of the BOM because quite often it's the cost of the LiDAR, which is a big proportion of that. And all of these machines struggle to cope when the world gets too chaotic, when there's too much dynamic motion. And this also tends to be because of the Lidar. So we restrict deployments to very controlled and structured environments. Now, just to be clear, I'm not against Lidar. I think Lidar is a great technology. The physicist in me loves the purism of this technology. And I see it as an extremely important sensor for safety. And the data provides really useful data for the perception stack. But I don't believe it should be the central pillar of a perception or autonomy stack. It should be a complementary sensor. Now, there's a reason why nearly every animal on the planet uses vision as its main sensing modality. A simple camera provides all the information required to answer these three questions. But the challenge has always been, how do you access this information in real time on affordable hardware? And how do you do this in a consistent and reliable way? So let's just take it one level at a time and I'll explain exactly how you can use a single camera to tackle these three questions. So positioning. Positioning is ultimately a set of numbers. It's your coordinates, your X, your Y, your Z, and maybe your pitch, roll, and yaw. These coordinates need to be relative to the static world, otherwise they're no use. And GPS is a great example of a positioning system, but it relies on highly expensive and complicated infrastructure of satellites, and it's actually very limited when operating even in outdoors within built-up environments, and good luck getting it to work indoors. Now, to explain how you can use a camera for this, I have a somewhat simplified example, but the principles can scale to something much more complicated. Now, we start by powering up our robot in a space that it's never been before. It has no prior information about where anything is or where it is within the space. Our robot has nothing but a single camera to sense the world, motor-controlled wheels to move around it, and as for today, of course, an ARM processor to crunch all the numbers. So what algorithmic logic can we use to tackle this first question? What is the position of the robot as it moves through space? So the only information it actually has available is the physical location of the individual pixels in its camera sensor and the corresponding color or intensity that they measure. And in this 2D example, we can project this information from the CMOS sensor to a 1D line, which represents the full output of the sensor. The intensity of each pixel and its location is shown on this line, and this really just makes up the view of the robot's world. So the first step is to select sections of this image that we can recognize as unique, irrespective of the angle from which they're observed. And I'll go into more detail about how we actually select the best features later. But in this somewhat forced example, the best candidates here are clearly the red bars on the blue boxes. So because we know the location of the pixels in the CMOS sensor, we know the distance between the pixels that correspond to these features. So this gives us relative angular position of these features in one dimension. And we can store this information in a probabilistic model which represents the location of these features relative to each other and the robot. But with just one single image, we don't know how far away these features are. So here they are just represented as 3 lines. The next step is to move the robot, and because the camera is mounted on the robot, the camera moves as well, and we repeat the process again. Now, because we selected features that can be identified as unique, independent from the angle of which they're viewed, we're able to identify the same features as before. Now, if we are able to measure the distance between because we've moved the position of the camera, the position of these features will have moved relative to each other. And this is really because of parallax. Just like when you hold your thumb up and move your head, the background appears to move less than your thumb. This is directly proportional to the distance away from the observer. This is the rule of parallax. And we can use this information to update our probabilistic model. So now previous positions of the features are no longer possible, and others are more possible. And you can see how the more we move the robot, the more we take these measurements and observe these unique features, we can start to build a fixed model of the location of these features, and we can in turn use these to triangulate the position of the camera. And this is ultimately how we can use a single camera to calculate the position of the robot and track its position through space. Now, what I'm describing here isn't revolutionary. This is a new concept. It was revolutionary back in 2003, though, when SLAMcore founder Professor Davison first released MonoSlam in 2003. This was really one of the first real-time single camera SLAM systems that would work just out of the box with a webcam and a laptop. And here we see actually what's become quite an iconic video in the world of visual SLAM. And there's Andy on the left, 20 years younger. And the principle he's demonstrating is exactly as I described earlier. On the left, we see the natural features being identified frame to frame. And on the right, we see the probabilistic model being built up, all in real time. The ellipses represent the error in the position of the features. And as you can see, as these are observed from more angles, the ellipses reduce in size until they become fixed in space. And this creates a sparse point cloud from which we can use to triangulate the position of the camera. Now, you might be thinking, hang on, I thought we were talking about positioning, not mapping. But the truth is, you can't have one without the other. So as I said at the start, a position is just a bunch of numbers, but these mean nothing if they don't correspond to a fixed reference frame. And that's what these features provide. Now, this is what SLAM in SLAMcore stands for: simultaneous, localization, and mapping. It's the process of building a map of one space whilst at the same time positioning oneself within that map. You can't have one without the other. Okay, let's jump into the architecture of this system and use this to show how we can tackle the other questions. So here we see the basic architecture of this visual SLAM system. Live images come in, and then natural landmarks or features are detected and tracked from frame to frame. And there are lots of different variations of detectors and descriptors. And we could have given our entire talk today about the different approaches, but we'll save that for another day if we get our invite back. For now, I'd like to quickly highlight the main common algorithmic characteristics. Now, feature detection is essentially it's a dimensionality reduction, typically going from millions of pixels down to hundreds of points. We may pre-process the input image to provide multi-scale representation for enhanced robustness, but ultimately, feature detection is performed in the same way on every pixel. So this means the compute operations can usually be parallelized quite easily. We can also use integer operations. They're often preferred due to the low power requirements. However, some parts are best done in floating point depending on the hardware platform being used. The operations usually work in a local window, so memory access patterns tend to be quite localized. And good choices for this hardware are the CPU with vector extensions, GPU, or DSP. And we're happy to go into that in more detail in the questions. Now, we're very fortunate at SLAMcore because we have two of the absolute world leaders in this space. Co-founder Dr. Ludenegger and CTO Dr. Alcantara are authors of the two most popular open source feature detectors, Brisk and Akaze. So as you might imagine, this is a key part of our core expertise and IP within the company. But by detecting the right features and positioning them as a whole, we're able to build a sparse point cloud from the size of a living room to a warehouse in real time to centimeter accuracy. And this is actually a sparse point cloud here. It's built 20 by 20 meters room, and it's just a few megabytes big. Now, this part of the process is computationally heavy. Serial dependencies mean the operations are more challenging to optimize. And it's difficult, it typically requires floating point precision to maximize the reliability. So optimizing for different architectures requires a lot of work. So it's often best to run on CPU to maximize the portability between different platforms. Okay, so I'd like to now go into my first demo, which really shows the full pipeline of the positioning system running in action. And this is actually SLAMcore's core product. We call it SLAMcore Position. So, okay. So I'm just going to jump to my camera so everyone can see me. So for the sensor today, I'll be using the RealSense D435i. This unit has multiple cameras in it and also has an inertial sensor. So to increase the accuracy of our position estimates, we will use 2 cameras, and we'll also use the gyroscope and accelerometer. And the details of how we fuse this information together is also fascinating, and I think would be a great topic for another technical workshop. But we'll save that for now. We'll also be processing the algorithms today live using the ARM CPU on the Jetson Xavier NX. So the latest edge single board computer from NVIDIA. Now, to be honest, for this demo, this is actually was really over the top. We're not using the GPU at all. We're just using the CPU. But I wanted to use something where I can show you more advanced features later. So I'd also like to introduce you to Barry. So Barry's going to be my glamorous assistant for today. He'll be the physical platform that we use to demonstrate everything in action. So he's just going to show you that he's working there. So, okay, and as you can see down at the bottom, we have the D435i, we have the Jetson NX, we also have the RealSense D455 on the top, which we'll use for later demos. So let's jump to the view from Barry. So you can see this is live now. Okay, so when we boot up the system, we just click start here, then the system automatically starts to process the images from the RealSense. Here we can see them being tracked, and as I move, they appear locked and anchored in real space. As we move, we start to make these measurements and start to position Barry relative to these features. So I'm going to ask Paul to actually take Barry for a little wander, and I'll describe to you what's going on. And let's change our view so we can actually see. So here we see the features being positioned in 3 dimensions, as well as the position over here of where Barry thinks he is in 3D space. The yellow line is the trajectory, the previous positions where he's been. So, but you must remember, I've not provided any previous information to Barry. He has no idea what the shape of the world is right now. This is, when we turned him on, this is all brand new. All he has to work with is the data generated from the Intel sensor that's on board and processing it with the ARM CPU. So as well as positioning the features and Barry within this map, our algorithms are also constantly checking to see if they recognize somewhere where they've been before. This provides additional information to the system because we know that if the view is the same, then the position should be the same. And if there's any discrepancy, then this has to be attributed to drift. And drift is inevitable. You just have to accept it when you're using consumer-grade sensors. But we can use this information to not just update the current position, we can also backwards propagate all of the measurements previously taken to take this into account. This is called loop closure, and it's a really important part of a Vision SLAM system. But you can imagine how and actually you can see right now the point cloud is being constantly updated and adjusted. You see little micro changes of all the positions as a loop closures are triggered. But you can imagine how the complexity of this becomes very high because every time you get more features, you're comparing it to the previous one. And this grows exponentially with the distance traveled. So to manage this, we have a lot of skills and approaches to doing that. And again, that's probably a topic of another conversation, and it's a key part of our core expertise. Okay, so if we bring him back, and I'll take the controller. Thank you very much, Paul. And let's just jump back to the presentation. So the map you just saw is vital for calculating position, but it's not really useful for anything else. The points are too spread out, and you can't use that for path planning or obstacle avoidance. You're just going to crash into everything. So they do provide a vital skeleton, which we can use to build a much richer map on top of. So the second level of spatial understanding is when a machine is able to understand the surface geometry of the world around it and build that geometry into a digital twin or a virtual model of the world. So back to the architectural diagram. To do this, we need a depth map. Now, a depth map is similar to a normal image, but instead of pixels corresponding to the intensity of light detected, they correspond to the distance from the sensor. So this might look like an infrared image. It's not at all. It's just measuring distance away from the camera. Now, there are a number of different sensors that exist purely to calculate depth maps, such as time of flight, Lidar, or even ultrasonics. But the problem is if you introduce more sensors to the mix, you need to perform accurate calibration, synchronization of the data, and this adds error and complexity. You can actually use the information from a camera to calculate a depth map. And using approaches very similar to what I just described earlier for calculating the positions of the key features, we can apply the same principles to every single pixel that's coming from the camera. The problem is it's hugely computationally expensive. Good news is, in general, it's very parallelizable. So it can work well with most integer operations and has localized memory access requirements. So due to the parallel nature of the algorithms, they can run on CPU, GPU, DSP, and excitingly, we're starting to see dedicated hardware for depth maps right next to the camera or even integrated into the system on a chip. In fact, this is how the RealSense camera calculates the depth. So if we switch to the camera mode, because I'm actually using a RealSense right now to talk to you, and I will switch on the depth map. So the color, as I said, relates to the distance away from the camera. So as I move my hand closer, you can see it going from blue all the way to orange. And to increase the quality of the depth map that's being generated, Intel also use an infrared projector, which provides more texture to allow the images to be processed. But ultimately, the principles are the same. So you can actually see down at the bottom there, you can sometimes see there. In fact, yeah, Barry down there, you can see the infrared projector flashing as the texture is being provided. So this depth map is computed on the sensor, and it streams straight out of the USB 3 connection. So although it's very computationally expensive, it doesn't matter because it's being calculated on the device, so we don't have to worry about it. So from our perspective, as long as we have a decent depth map that's calibrated and synchronized with the data that we're using for positioning, we can then fuse that same data together and create a reconstruction of the world all in real time. In fact, here's a model that you can see that was built with our system. But it's absolutely definitely better to show you this live. So for my next demo, we'd like to actually take Barry for a bit more of a wander. Okay, so let's just switch to his view. So just to show you it's live again. Now, again, here we have the view from Barry's camera, but as we move, we can see the digital model being built in real time and overlaid onto the real world. So we're actually representing the world here as a 2.5D map. This is a height map, and it's representing occupied space as a series of pillars. Okay, but I think the best thing to do is actually go for a bit of a walk, and I'll show you this mapping out our office in a lot more detail. But before I do that, let's just zoom out so you get a good view of what's going on. Okay, so bear with me. I'm actually going to get up and go for it. So I'm now going to give Barry a tour of our offices. This is, and actually I'll give you all a tour of our offices if you see the images in the bottom left there. And I think the important thing to really remember is I've not loaded any previous information whatsoever into this, into Barry. This is the first time he's ever seen this space, and the data is just being processed live. All that we have available to us is the information from the RealSense camera and the ARM CPU to crunch the numbers. Now, 2.5D maps are really useful for ground robots because they provide all the information they need to get from A to B safely and to avoid obstacles along the way. It's very memory efficient, and we can map an entire warehouse with just a few tens of megabytes. Okay, so you can see that it's all been built live. I'll just give you a bit of a, you can see this is it's 2.5D height map, all built in real time. But the reality is most robots don't operate in just an office. Sorry, they don't operate in the places they've never been before. And they also tend to operate within fleets. So the great thing about maps and position based on vision is that they can be shared across compatible machines. So what I'm going to do is load a map that I built of the offices last week. So this was actually built with a totally different lighting conditions. The world has changed a lot since then, as you'd expect, as we've been moving things around. But now, when we launch the system,
we're now running in localization mode only. So what we do is start to try to recognize the video and the features being detected from the live view and compare it to the map that was built a week or two ago. And here we go. All we had to do was go for a little, just give it a few features to detect, and it's managed to recognize its position. So now we are no longer adding to the map. We are just measuring our position and providing that within the reference frame that was built last week. And because we're just using the passive cameras for this, there's no real limit to the number of robots that can operate within the same spatial reference frame. Okay.
So Paul, so what you're saying is once the robot is kind of determined or detected a location, you can load a reference frame, and then anything that's new or different, it'll pick up real time. And will it add to that reference frame, or is it just, I guess, can robots remember the space that they've been in before?
So the space that the map that we've built there is unique to the space, not to the machine. So
Right.
as long as we have another machine which it has the same is compatible hardware, so another RealSense, it's able to take the live measurements and compare them to the measurements that were taken from a previous map, and this allows you to position yourself in a map that was built a week or two ago. And this means this is a much more computationally efficient way of doing that. And it allows multiple machines to all present their coordinates in the same spatial reference frame.
Cool.
Okay. So, but 2.5D maps are not, are great for ground robots that operate on a ground plane, but they don't always deliver the amount of data that you need if you're a drone or a wearable. So this extra dimension is what you really need if you want to be able to fly around, or if you're an augmented reality or virtual reality headset, you need to be able to build your world in 3 dimensions. So this is now my final demo I'll give with Barry. So we're just going to jump into the 3D viewer now, and I'll just move it on to the view from the camera. One second. Are there any questions while I just set this up?
No questions yet. I think everybody's mesmerized by watching Barry do his thing.
Good stuff.
I know I was like, oh, that's so cool.
Okay, so. Okay, let's go. So same view as before, but now, and we'll start to render the world. The key difference now is we're not representing the world as a series of pillars. We're representing the world as, and I'll just remove that plane. We're representing the world as voxels. So these voxels can be varied depending on the computational resource that is available. I'm just going to turn the sparse point cloud off because that becomes quite distracting. And if we jump to the 3D view, we can go for another wander, and you can see this being built in 3 dimensions, all in real time. And just to remind you once again, this is just using the data from the RealSense camera and the ARM CPU of the Jetson NX. And one of the real nice benefits of using vision as well is we have access to the color data as well. So we can not just represent geometry, we can also provide color and texture into the map. Okay, so as we start to move, you can see this map being built. So I know I keep saying it, but there has been no previous information provided to the robot whatsoever. This is all being calculated on the fly in real time. The only information that has available to it is from the 2 cameras on from the RealSense and the IMU, so the accelerometer and the gyroscope. Just change the view so you can see what's going on a bit. So just as a reminder, we're taking all of the natural features from each frame, comparing them from frame to frame, and positioning them in 3D space, and using that to triangulate the position of the robot relative to them. That provides our sparse point cloud and essentially the skeleton for this map, which you're seeing emerge. And then we're taking the depth map from the RealSense camera, which comes straight out the USB connection, and the color data from the same camera, and rendering it all in a single model. And because we're only using the CPU from the ARM device, it means we have a lot of headroom left for some of the next generation algorithms, which is where I'll finally finish my presentation with you. So let's jump back into the presentation, and we'll move on to the final level. So so everything I've shown you up to this point was representing the world as either series of points or surface meshes. Yes, we had color, but ultimately it was just geometry. The world, as we all know, is made up of objects. It's not just shapes. And depending on what those objects are, we might behave differently. And we want to have the same type of actions from our robots. If there's people around, they might want to behave in a different way. If there's other robots, there might be some different type of behavior. So this is really where the final level of spatial understanding comes in. So I'm sure you're all familiar with videos like this one. The last few years have seen an explosion of companies who provide neural networks for object labeling and powered by huge advances in both the hardware and the software. But CNNs require extremely high levels of compute, but there's also very high levels of parallelism. So typically they're trained in floating point, but are often able to map down to integer to reduce memory size, bandwidth, or computer power. And operations mostly rely on lots of local memory access. So just to give you a bit of technical background, they can be run on GPU, but we're starting to see the emergence of exciting dedicated neural networks, neural network hardware blocks such as MPUs. So this is really exciting, especially for edge devices, because once you start to be able to label the 3D space, we're able to actually use this information to enhance the entire performance of the system. So here's actually the SLAMcore proprietary panoptic neural network. This has been a number of years in the making, and it's been designed to be accurate, highly efficient, and very transferable between different domains, which is normally one of the real challenges for neural networks. Again, we'd love to come back and tell you more about this through another technical talk. But for now, I'd like to show you how we can use this as part of the wider system. So because we're using literally the same data that we use for the positioning and the mapping, we can then fuse that data into the wider system. So the first big benefit is we can pass that data right the way back to the start and apply the semantic information to the measurements that we're taking for those features that I talked about earlier. And here we actually see this is actually our system running on, it is an open source data set, but it also works with recorded data sets. And we can see how we're able to reject the features that are detected on dynamic objects, such as people, and in this slightly odd example, a huge teddy bear. So this really does improve the performance of your when you're in dynamic environments, and it means that we have, because that is the start of the entire stack, it improves the performance of the mapping and also the confidence of your object position estimates as well. So we can also combine the semantic information into this 3D demo that I showed you earlier. And here we really are seeing a glimpse into the future. This is something that we've never shown publicly before. And I'd like to actually show you some of it running now. So full stack vision-based spatial AI is when we bring together all three levels of spatial understanding into a single system. And by designing and optimizing as a whole, we can deliver much greater performance than if we tackled each of these separately. So this demo I'll give you now is still in development, so do forgive me. I will be running it on my laptop. Instead of running live, I have a pre-recorded data set that I used, recorded from the Intel RealSense camera. But just to be really clear, I will be processing this data live. There's no kind of tricks and no renderings happening in it before this. Okay, so just booting up now. That was my bad. That was the live demo, which I will save that for another day. So we might be hitting the curse of the live demo here.
It wouldn't be a demo if it didn't work.
Absolutely, and that's that is such a shame. So I might have to just jump to show you this either at the end, or hopefully we can come back and show you this running.
Yeah, sure. We've actually had a couple of questions come in.
Sure.
So the first question is, what's the camera resolution and frame rate, and how sensitive is the accuracy of your algorithms to noise in low light conditions?
Sure. Paul, could you take that one? And
I'll sure. Well, you're trying to fix the demo. So camera resolution. So our algorithms are somewhat agnostic to the specific camera resolution and frame rate, but obviously for the demo we've shown today, we're running with the D435i camera, and we use, for the positioning, we use the grayscale IR cameras that are running at about 840 by 480 pixels resolution, and on the NX I think we're running at 15 frames a second. So we can run at 30 frames a second. For this demo at this sort of speed, 15 frames a second is perfectly fine. And so you asked how sensitive the accuracy is to noise in low light. So the feature detector and then the descriptor we use are pretty robust to noise at low light levels. I don't have any specific metrics to provide to you, but there's the kind of, before we do the detection and extraction, there's a bunch of pre-processing that's done, which helps to improve the robustness. And then I think, so there's another question, let's see in the questions and answers, which is, how does your localization system work? So I guess this is asking particularly about the demo where Owen captured the map and then was doing the localization against the map. So we, in that demo, what he was showing was create a both a sparse and a 2.5D height map in the same coordinate system, and so the feature points in the sparse map are what we then, when we're running in localization mode, we're detecting features live and trying to work out where in the saved map those features are. So there's lots of work going on kind of underneath the hood to make it as efficient as possible, but ultimately that's what we're trying to do, is for the features that we're seeing live, where were they previously? And so the detectors and descriptors that we use have quite a lot of illumination invariance and robustness in them, so that we can we can build the map under one set of lighting conditions, and then under a different set of lighting conditions, we're still able to localize.
Thanks, Paul.
It's quite a high level answer. I think, as Owen said on a number of occasions, we probably spend a lot of time going into a lot of the technical detail. We don't have the space in this talk to go into the low level details on. So that the localization.
Yeah, well, maybe when you come back, we can do a deep dive, a technical deep dive. We have another question, which is, how much power does it take to run your algos on ARM CPUs?
Okay, so that's a good question. So I think obviously it depends on the specific CPUs and specific processors. But so typically so we're using the Xavier NX here, and typically at a system level, we're seeing when everything's idle, it consumes sort of 1.5 to 2 watts. When we're running our algorithms fully, it's kind of in the order of 4 to 4.5 watts. So somewhere, and all of our algorithms are running on the ARM CPUs. So it's in the order of a couple of watts that we're using for our algorithms.
Great. Thank you. And I just wanted to open it up. If anybody wants to ask any direct questions, the time is now.
Good. Actually, I'm all right. I'm gonna.
Oh, did you figure it out?
For completeness, I'm going to show you a quick video of this system running because I feel I've left it a bit of unanswered.
Left everybody hanging.
So let's. This is a quick video just to show you this all come together. I recorded this earlier today just to show it's all working. This is a pre-recorded data set building the 3D map as described and as shown earlier. So we're positioning the camera in real time and building the 3D map using the voxels. But the key difference here is we're also passing through the semantic information through these voxels and creating this same map now, but all of the objects are labeled in real time. So this is all happening frame to frame. So it's something which means that if you wanted to, for example, we could remove all of the dynamic objects just with a single click. So as you see now, we can remove, this is one of our deep learning researchers, just by selecting them, and straight away they can move. We can remove the walls, the ceilings, and this is something which is really useful for roboticists because once you've built a map, you have to go in and tidy it up quite often because dynamic objects move, especially when you're sharing them from day to day between different machines. So this means you can do that straight away. But I think the more powerful application here is now that we have a system that knows the physical location in time and space of all of the objects within that map. And so you can imagine a robot which tells you where you left your keys, or probably more useful for industry would be a drone which is able to tell you the position of all of the assets within your factory. And this is something which is only possible when you start to bring together all of these different parts of the stack together in a full stack approach. And that's why really what we're doing is so exciting. So yeah, I thought I'd just show you that now so we can, for a bit of closure.
No, I love that. Thank you. Thank you. That's really great to see. We've had a few more questions come in, so let's motor through those. Visual SLAM is computationally intensive. How many cores do you need, and do you run in real time?
Yep. So I'll pick this one up. So it can be computationally expensive. We do run in real time. So everything that Owen has been showing today is like that's streaming live off the camera. It's absolutely running live. And so we also have kind of have a certain amount of kind of flexibility and we can tune the algorithms to different platforms. So so we can go down as low as kind of a couple of cores on a Raspberry Pi, all the way up to much more computationally demanding or computationally capable platforms. And so I think so on the NX here we're using on average it's around 2 cores, but we kind of have a load of threading going on, so at different times we'll be using different numbers of cores.
I think it's important with this type of the SLAM system. There are so many different hyperparameters and ways in which we can set things up that it's almost a question of how many cores have you got will give you the best performance for that. Because there's a huge. We can also look at porting to different like DSPs and different hardware accelerators as well. But just as a kind of a benchmark, yes, I think a couple of cores is a good place to start. But yeah, we have a team of obviously algorithmic developers, but also embedded software engineers, and working together, that's how you really get the best performance out of your system.
Yeah. Okay, you mentioned the semantic labeling was done with a neural network. Are there any other components implemented in neural networks?
Owen, do you want me to pick this one up?
Yeah, go for it.
Yeah. So today, no, right? It's just the semantic labeling today. Obviously, the whole world of computer vision is in general, a lot of stuff is moving to neural network-based approaches. It's certainly something we're looking at. Yeah, I think today it's, you know, the sort of the front end, the feature detection descriptors. It's marginal gains you would get from going to a neural network. They're not showing massive performance advantages, but it's absolutely we're working on it, looking at it, but not today.
It's been really interesting seeing the emergence over the last 10 years of this, like CNNs into particularly the vision-based SLAM. And there was a period where it was almost like you had to be in one camp or the other, and it was neural net end-to-end trainer system. Why would we ever hand code geometry into a system? Let's learn everything. And I think, yes, there are some people who still argue that, but the way we see it is they are a tool to be used as part of your design, and they should be used for the parts that make sense, and other parts you actually will have much better, especially when it comes to transferability between different domains and things, then actually that's where they really start to hit their limits. So using it for object recognition is kind of a no-brainer, really, but there are parts of the stack which are quite well suited to this type of design, and yeah, we have active research into those areas right now. So the great thing is, once we have our system, we can keep on updating it and making the new features available as we learn how well it performs in different domains.
Great. Okay. Next, how do you detect dynamic objects? Is it by measuring frequency?
Today, it's really an association with a class. So we know that people are likely to move, right? So yeah. we're not doing any on the fly analysis to say, is this likely to be a dynamic object or not? Now, within the SLAM algorithms, there is a bunch of stuff that tries to determine if there are inconsistent motions within the object, within a scene, and tries to ignore the inconsistent bits. But then when you bring in the semantic layers, it's kind of a hard association between the class and the dynamic object.
All right, next question. We have a few more. I think we have enough time to get through all of these. So looking at the feature points, does the system consider them in the same way, those which are closer and those which are further away from the camera, and any distinction when processing them?
So I think yes. There is there's a whole bunch of analysis and work that we do to decide which of the features we use and which ones we don't when we're doing our positioning and mapping. Yeah, lots of energy in the company, and lots of research goes into that. How do we know when a feature point is good? And actually, there's a certain amount of contextual situation. So knowing, you know, there's certain characteristics that you may have inside to outside, and so there's a whole bunch of different different information we take into account, trying to make the best SLAM system.
As you might, there's probably, we start to get into the probably quite commercially sensitive elements of the technology there, but that's one of our real expertise, is because a SLAM system is only as good as your features that you are building it from, and also whether you can process them on in real time on low cost silicon. So that's something which is fundamental to the system, and something we are very, very proud of, and that's why we're able to build maps of warehouses for just a few megabytes and do loop closures across that size, because we have designed those that not just the features but the way in which they're stored and optimized. It's a huge area of research and expertise for us. Sorry, it wasn't a direct answer, but
so yeah, the next question is how expensive are the sensors we need, and can we run with low cost sensors? So yeah, there's really, so the core of what we're doing is there are two sensor modalities. One is the image sensors, the other is the IMU, and we're kind of it's sort of mobile grade image sensors that we're working with, right? So it's not there's nothing particularly sophisticated or elaborate about the core sensors that we're using.
I tend to say we're not hardware agnostic, but we are hardware portable, because hardware agnostic just means it's bad on everything. So as long as we have images and IMU data come in, and we can work with that, but we've optimized for specific sensors which are available readily on the market. So, this is where we can tune depending on what's available. So if it's a bit like my previous point, you tell us what hardware you have available, we'll give you the best SLAM system for that. Although if we do that for every customer, then we're just a consultancy. So we have a kind of off-the-shelf experience that you can use using sensors which are available today in small and high volume.
Three more questions. So let's try to get through these. So yeah, thank you everybody for sending these in. It's really great discussion. So how does your software using cameras compare with Lidar systems?
Maybe I'll talk about just the kind of the pain points that a lot of the as well as cost. I think there's a common one we are told with Lidar systems, and we've observed ourselves. One of the real challenges is the dynamic environments, because most of the Lidar systems used today in robotics are 2D single plane Lidar. In fact, Barry has a 2D Lidar for safety reasons, which is a tiny slither of the world. It's taking very accurate measurements, so it's good as long as the world is all very constant, and but it's got a very small amount of the world to actually measure against. So all you need to do is quite often move a few boxes, or move maybe even another robot or a person walks around, and it starts to take measurements from that, and that really creates essentially a loss of localization. That's a hard one to say for the system. So I don't think it's either or. It's not Lidar versus camera. Like Lidar has failure modes, vision systems have failure modes. The best is actually when you start to bring them together, and you can use the best of both worlds. But our central argument is that the pillar of the system should be vision. Complementary to that would be Lidar.
Next question. Do you do some extra processing when using your systems outdoors?
No. Ultimately, just like humans, we operate. We can go indoors, outdoors. Yes, there is also different exposures maybe required. That's more of a hardware setting for the sensor, and by quite often things outdoors are maybe further away. So there are maybe some tricks we could use there. But ultimately, we're just using the world around us to position the robot. So as long as there's things to see, there's texture, there's objects, then indoor, outdoor, as long as the sensor data is able to read that information, then we can process it. So yes, there are definitely kind of tricks and tactics you can use, but I wouldn't, it's not indoor versus outdoor. It's much more around what's your lighting and what's your environment.
Yeah. All right, last question. Could two maps generated in two different but adjacent regions be connected together by a machine traveling between the two regions?
Yes, I love that question. It's really where the power starts to come in together, because, like I said, the maps are unique to the space, not to the machine. So as long as the machines are compatible, yes, these spatial information can be shared. You can build with one map. The robot can then operate within that map that was built by a previous robot, but also you can merge them together, and you can start to actually create much larger maps or manage them in a way. This is something we don't support out of the box right now, but we have a system in development around that.
All right. I think we did it, guys. Thank you so much. That was a really great presentation, and
absolutely.
Thanks. Yeah, that was awesome. That was a really great way to kind of round out our year 2020 for Virtual Tech Talks. So really appreciate your time. Thank you everybody for attending. And we will be making this presentation available on demand the next day or two on our developer YouTube channel. So head over there if you want to see this again, or if you have friends that you want to point over there to check it out. We'll also make this deck available. There we go. So yeah, so here's how you get a hold of us. So there's the ARM YouTube channel. We're going to be publishing our 2021 schedule shortly, so watch this space for our upcoming presentations. And again, please fill out the survey and let us know what topics you want to hear about. Let us know what things you like, what you want us to stop doing. We really love bringing these topics from our partners and our ARM engineers to developers. So this is all for you. Please let us know what you think. And I think that's it. We'll sign off. Thanks again to Owen and Paul from SLAMcore, and happy holidays, everybody. Stay safe out there, and we'll see you again next year. Cheers.
Thank you so much.
Thanks,
Thank you.
Mary.